From the beautiful studios of Way Happy, this is Mr. Meyer in section 11.1 combinations and permutations. Now, eh, before we get started, this is a whole class in college, right? This is combinatorics as a class in college, and you're going to spend about a week and a half, 2 weeks on it. So be prepared. It goes kind of quick, it gets kind of confusing, and you don't get a whole lot to sink it in. But hopefully, after this, you at least get an intro to it and you feel a little better. So let's start off with the fundamental counting principle. And the counting principle says that if there are n items and m ways to do this, right? The first item, and then there's so many m2 ways to do the next item, and keeps building on that. Then all you have to do is multiply these all together, and that'll tell you how many ways you can make it. Now, let's try to make more sense out of that. If you had 3 pairs of pants and 2 shirts, you would have 6 different outfits that you could make, because you could wear one pair of pants with all 3 shirts, or the other pair of pants with all 3 shirts, or whatever I said. And so you just multiply those 2 outcomes together, and that's what the fundamental counting principle says. It says if you're going to do these things in order, and there's that many ways to do something, then you just multiply them together. So, like here, look at my first example. You're going to make a parfait, and you get to pick a flavor of yogurt, and then a fruit, and then a nut, one of each, right? So when you come over here to pick your flavor, you got 2 choices. And then you come over and you pick your fruit. Well, this place has 5 choices of fruit. And then they have 3 different types of nuts. So guess what? You got 30 different outcomes, or 30 different parfaits that you can make. Now, a little heads up, if that's like, wait, no way, how could that be 30? One thing that helped me a ton through all of this was being able to make what's called a tree diagram. And even though this section mentions nothing about it, I'll show you kind of how you do it. And it would be kind of messy with this one. But you start off that you could either pick plain yogurt, you just go order by order, or you could pick vanilla, right? And then after you pick that, you had peaches, strawberries, bananas, raspberries, and blueberries. So peaches, strawberries, bananas, raspberries, and blueberries. And then after you chose that, you had 3 different choices of nuts to put on here: almond, peanuts, or walnut. Almond, peanuts. And that would, you know what this does? This shows you every single outcome that would happen. So you could have a plain with peaches and almonds, or you could have a plain with peaches and peanuts, or you could have a plain with peach. See, right there's 3, right? Different outcomes. And you'll see that you'll have 3 here, and 3 here, and 3 here, and 3 here. You'll have 15 outcomes here. And then we haven't even talked about vanilla. So vanilla is going to mimic that exact same 15. And that's how you're going to get 30 different outcomes. So tree diagrams help me see every single order that you could make. And the counting principle is kind of a shortcut to that. It's like, hey, count these up and tell me how many there are. So hope that clears that up a little. Now, what about this? You have a password, and it is 4 digits followed by 2 letters. The letters A and Z are not used, and each digit or letter, it should say, may be used more than once. So how many different passwords can you make? Well, you have to think of what you're allowed. You're allowed to do a digit and a digit and a digit and a digit. So these are all digits. And then I'll put D's. And then you got to pick a letter. So we'll put an L for a letter and a letter, but not A through Z. So be careful. Well, think about digits. You can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 different outcomes for that. So a digit has 10. Now, they said I could use them more than one. So I could have 0, 0, 0. So that's cool, or 1, 1, 1, or whatever. Or 1, 1, 2, 2 is fine. So guess what? There's 10 digits for each one. Each one I have 0 through 9. Now the alphabet, there's 26 letters in the alphabet, but you're not allowed to use A or Z. So we're going to have to take those out. So now there's 24 letters. We are allowed to repeat. So you have 24 options and 24 options. This would be a huge tree diagram, which I don't want to do. But that very first option would have 10 options, right? And then it would have 10 options off of there, and 10 options off of there, and 10 options off of there. Then 24 options off each one. Oh my gosh, it'd be insane. So good thing we have the counting principle. But you can imagine you would have a ton of what they call leaves on a tree diagram. Those are all the leaves at the end, and those are like how many outcomes there are. And there you would have whatever the heck that is. This is 10 to the 4th times 24 squared. And I guess I should get you that number. So I will fire up virtual Sheila, and I will ask her to do that for me now. So I want 10 to the fourth times 24 squared, and it's going to be ginormous. Holy macaroni. I think it was 576,123. Was it 576,000? No, geez, 5,760,000 different combinations of passwords. So just by giving you 4 digits and 2 letters, and we ask you to make a password, you could make that many passwords. All right, let's give you a question, and I'll see you after the break. All right, good effort on that one. Now let's move on to factorials. All right, now factorial is this, right? Factorial means exclamation mark. N factorial looks like that, right? So this is read as 3 factorial or 7 factorial. Now, what does a factorial mean? It doesn't mean scream the numbers like 3 or 7, right? It actually means something. It's the product multiplying all the numbers up to that number together. Starting with 1, all the natural numbers, right? 0 is not a natural number. So all your natural numbers, 1, 2, 3, 4, 5, whatever. So you can see here in their example from the book, 6 factorial is 1, 2, 3, 4, 5, 6, all multiplied together, and you get 720. So math geeks didn't want to write that all out all the time. So they exclamation mark. That's what that'll mean from now on. So you can see here, and on my side too, I have 4 factorial is 4, 3, 2, 1, all multiplied together. A very important one to know is 0 factorial by definition is 1. So I know that you're saying, wait, 0 now it's a definition. They said, all right, 0 factorial means 1, and that will be understood by the world. And we say, okay. So there you go. Factorial is just you multiplying everything together. So you got 5 friends. You guys are standing out at, I don't know, your favorite movie, and you're about to go in and you want to take a picture on Instagram so you can be like, hey, look at us. We're about to go in to see Star Wars, whatever. And so you guys line up and you take a picture. Did you realize how many ways that your 5 friends you and your 5 friends could actually take that picture? It's crazy because there's actually 6 of you, right? And so as you guys all line up, I have 6 choices to put the first person, like say they're going to stand against the wall. And I have 6 choices for the first person. And then I have 5 choices for the next person. And then I have 4 choices, and then 3 choices, then 2 choices, then what the heck, right? So that's what we would call 6 factorial, because you're going to do all of them. Now, this is when you use up everybody. Like you have 6 people and you want to put all 6 people in the picture. So then, boom, 6 factorial. That's how many ways I can write them up. I'm going to use everything I have and I'm going to put them in order. Notice it's a little different than the counting principle, because I guess you could kind of think of it as the counting principle. As you take a person away, you're like, well, how many are left and how many are left? So you could think of it as the counting principle, but it's different as we're taking all 6 people and we're lining them up in a line and we're finished, right? There's not different categories like we had in the first example. It's just all 6 people lined up. 6 factorial. Your calculator loves to do this, right? You could type it all in, or you could just type 6 and then go to math over to probability, the PRB, and look at number 4. It's an exclamation mark. And so when you hit enter, it says 720, and you're like, what? That's crazy. They're unbelievable that you guys snapped that picture and you didn't even take the time to think there was 719 other ways we could have arranged ourselves. That is amazing. And you just picked one. So crazy. Anyway, try that the next time you're out there with 5 of your friends. Now that's when you use everybody up. Now we got a permutation, and a permutation is a bit different. A permutation is when I'm going to only take a picture of a couple people. Like maybe there's 6 of us, but I only want 3 of us in the picture. So how many ways could I put 3 of us in there? I could take the first 3 or the last 3 or every other person, or you don't know what you could do. So there's a bunch of different ways. So we'd like to count up all the different ways. So now the most important thing you want to know about a permutation is that it is when we use it when order is important, right? When it matters if Billy was first and Sally was second would be a different picture than Sally first and Billy second. You have to decide. You're the math person. You're the person looking at the data. You decide, does order matter in this problem? I'm going to have to use a permutation then, aren't I? but it's only when you're picking a group from a group. It's got a funny way of writing. NPR looks like that. Look at the equation: n factorial over n minus r factorial. Cray cray, right? Or as the way I explain it, ways to arrange everything over the ways to arrange things not selected, because we're going to divide them out because they're not in the picture. So that is called a permutation. So look at my example. How many ways can a student government select a president, vice president, and secretary and treasurer from a group of 6 people? So you got this club that has 6 people and you want to have apparently 4 positions. Now you got to decide, does the order I pick them matter? Because if I say Sally and Billy again, so Sally's president and Billy's vice president, would that be different than if I would have gone Billy Sally, where Billy is president and Sally is vice president? Well, yeah, that's different. Look at their titles. They're different things, right? One's a president, one's a vice president. So now I realize order is important. So order matters, right? So that's the first thing I notice. So I'm going to use a permutation. Now I know I'm got 6 people, but I only want to pick 1, 2, 3, 4. So I'm going to do 6P4. Or by the way, some calculators and people will do it like this. They'll have like a P and then they'll go 6 comma 4. That's what you would do on Wolfram Alpha or in some other websites. But so be careful. There's 2 different ways. You say permutation, then the total number, and then how many you're choosing. Now, what does that look like? Well, that looks like 6 factorial over 6 minus 4 factorial, or 6 factorial over 2 factorial. And if you want to think of that in math, 6, 5, 4, 3, 2, 1 over 2, 1. You kind of cancel some stuff out if you had to do this by hand. And you would just get, what is that, 30 times 12, 360 or something. So let's see, I'll show you on your calculator too. I can do a NPR button. So it goes 6, and then I go math over to probability and look at number 2, NPR. And we are choosing, what we say, 4 things. So boom, hit enter, 360 different ways that we could take those people and put them in a club. Now I know that's probably blowing your mind. You're like, wait, really? Really? There's only 6 people and you want to pick 4? You could do that 360 ways? Yeah, if order matters, right? If order matters. That's the way to do it. Making a sandwich and you have 6 toppings and you can only pick 4. There's 360 different ways that you could put those toppings on your sandwich. Now, does order matter on a sandwich? I don't know. It's up to you again. We'd have to argue about that. Look at this one. How many ways can a stylist arrange 5 of 8 vases from left to right in a store display? So again, I'm going to say, oh yeah, if the roses come first and then the daisies, that's going to look different than if the daisies come first and then the roses. So I'm going to say order matters. And then I'm going to go ahead and figure out how to do this. So I'm going to say, all right, you got 8 and you're permutating 5 of them. So 8 factorial over 8 minus 5, that's 3 factorial. Now I'm going to go over to Sheila, or I'll do this by hand, but that's going to be, no fun at all. 8 math over to PRB. Oh, I picked the wrong one. Don't you hate that? Math over to NPR. And we said, what is it? 5. Boom. 6,720 ways. Now, if you want to make a tree diagram, if you don't believe me, that would be a lot of leaves, though. But that's how many ways they could arrange it. And I know, hard to wrap your head around. Crazy. See you in a minute. Excellent work. Now let's wrap this up with combinations. Now, combinations are, a minute ago I talked about a sandwich and the toppings going on the pizza, or on the sandwich, and order mattering. And you might have said, you know what, it doesn't really matter. Then you would use a combination. If you feel, or maybe the order, you can't determine it. If you feel that order doesn't matter, then you're going to use a combination instead of a permutation. So combination and permutations, when you're selecting a group from a group, right? You're not using everything. You're selecting a group from a group, and you're deciding if order matters or order doesn't matter. And then you're going to tell me how many ways you can do that. So you can see the formula here. You can see a combination, very important. Order does not matter. The way I remember that is, I think combination pizzas, the order doesn't matter how you throw the toppings on there because it's a big mess anyway. So combination pizza, order doesn't matter. So that's why combinations, order doesn't matter. Now the formula for it, not too different. You can see right here, if I highlight this is the permutation formula. And then we add on this little R, because that takes out all the things that we repeated, right? That takes out all the ones that had the same group of people in them, or the same toppings for your sandwich or whatever. This makes me always think of Mr. Conover came in one day. He was coaching his daughter's, U6 soccer team. And he's like, I got 12 girls on the team. How many ways can I put all four out there? Because he wanted to make, I got to put four of them out there. How many different combinations are there? And I had to decide if permutation or combination was the best choice. And as we talked a little longer, I realized that in the U6 soccer, they don't really have positions, right? He just throws four out there and they run around and try to kick a ball as best they can. And so they didn't really have position. They weren't going to play them anyway because they didn't know what they were. So he just needed a combination. So order didn't matter. Now, if I was doing it with high school, it's totally different because you got, wingers and center and defenseman and a goalie. I mean, it's totally different thought process there. But here, order doesn't matter for him. So I just said, hey, let's do a combination real quick and I'll tell you how many different ways and you can start charting out all those different combinations. It's the same thing here. You see my example. There's 12 different cubes in a bag. How many ways can you pull out four of those cubes? Now, again, they're all different colors. So when you pull them out, if you pick out red, green, blue, and yellow, is that different than green, blue, red, and yellow? No, because you just grabbed four out. I don't even know what order you picked them out, so I can't even decide if the order mattered or anything. So you grabbed out four and you're like, showed them to me. I'm going to go combination with that because I can't tell, the order that you picked them. So I would use what's called a combination. Order doesn't matter. Same thing and same numbers I had to use for Mr. Conover. Order doesn't matter. So I'm going to do 12 objects and I'm going to choose them, four of them. And so there it is. By the way, you'll notice this notation I kind of didn't mention right here. A lot of books will use that notation for combinations only. So you'll see NCR, you'll see the C with the parenthesis NR. A lot of calculators will do that also. So just be careful about what you're using. Our calculator luckily uses this, so it makes sense to us. So 12C4, I'm going to grab Sheila and I'm going to type it in. But if you're curious, what would that look like? That's 12 factorial over 4 factorial and then subtract them, 8 factorial. So the cool thing there, you don't multiply the 8 and the 4 together or anything. You have to do them individually. Think about what that is mathematically. 12 times 11 times 10 times 9 times 8 times 7. I don't want to do anymore. All the way down to 1 over 4 times 3 times 2 times 1 times 8 times 7 times 6. See where that's coming from? All the way down. Now, again, by hand, it's kind of easy because look, this 8765432 8765432 Heck, here's a 12. That cancels that out. And let's see, 2 goes into 10 5 times. So is that 99 times 5? Whatever the heck 90. So it's, what is that? 500, not quite. So it's 495. So this should be 495. Grab Sheila. I'll show you how to do it in there. You go 12 math over to NCR, so over to probability, down to number 3, and pick number 4. And there is 495 different ways that you could pull out 4 cubes from that bag, or Mr. Conover, there's 495 different lineups that he could throw out there and on his soccer team. So what did he do? He tried to figure out how to get every single one into a game. So he divided up how many minutes he was going to play. And he's like, I'm going to play these ones, that many times. And this, he's crazy, but he did it. And that's it. Combinations, order doesn't matter. Permutations, order matter. Counting principles, just multiply them together. And factorial is that crazy symbol for multiplying all the natural numbers together up to whatever number you want. Have a great day. Stay happy, and I'll see you tomorrow.